Say we had a function that starts at a, and at a it has the value of f of a, and ends at b, and at b it also has the value of f of a. And the function could look a lot of different ways, but one option is for it to go up and then go back down. It could go down and then back up. It could be a horizontal line. It could go up and then back down and then back up again. But it starts and ends at the same place. Well, one thing that's true is that if it starts and ends at the same place, then the secant line from A to B would have a slope of 0. And by the mean value theorem then, since this is a closed interval that's continuous and differentiable everywhere on the interval, there must be a point where the derivative, or the slope of the tangent line, or the instantaneous rate of change, will also be 0. Now this case, this specific application of the mean value theorem is called Rolle's theorem. And really, it's important that you just recognize that this is just a specific application of the mean value theorem. Right? Specific to Rolle's theorem is that if a function that's continuous on a closed interval and differentiable on the open interval starts and ends at the same y value, then the derivative must equal 0 at a certain point. But really, this is just the mean value theorem applied to a specific case. A different example, though, involving the mean value theorem, is we'll be given a function, f of x, equals 3 minus 5 over x. And what we want to find is, what's the value c that is on the interval 1 to 5, that just means that c is somewhere between 1 and 5, that satisfies the mean value theorem? Well, the mean value theorem relates the average rate of change to the instantaneous rate of change. So let's find the average rate of change. I'll find that in red. So the average rate of change is just the slope of the secant between the two endpoints. So the average rate of change in this case will be f of 5 minus f of 1 all over 5 minus 1, right? Just the slope of that line. F of 5 in this case would be 2. F of 1 would be negative 2. And 5 minus 1 is 4. So the average rate of change is 1. If it's going to satisfy the mean value theorem, what we're trying to figure out is, when does the average rate of change equal the instantaneous rate of change, or when does it equal the derivative? So I want to know, when is the derivative of my function equal to 1? Well, to take the derivative of this, I'm going to rewrite it as 3 minus 5x to the negative 1, so I can use the power rule. And the derivative of this is 5x to the negative 2 power, which is equivalent to, as I go to solve this thing, 5 over x squared. When will that equal 1? Well, that's going to equal 1 when x squared equals 5, which is when x equals the positive or negative square root of 5. But c, the value we're looking for, has to be between 1 and 5. So this means that the only possible value c can have is the square root of 5. Let's consider another example. F of x equals 2x plus sine x plus 1. We're focusing on the interval from 0 to pi. And we'd like to know what the equation of the tangent line is at the point which is the solution of the mean value theorem. Well, again, we need to relate the average rate of change. So in this case, that will be f of pi minus f of 0, right? The slope from endpoint to endpoint over pi minus 0. And f of pi, well, that would be 2 pi plus the sine of pi, which is 0, plus 1. And f of 0 would be 0 plus the sine of 0, which is also 0, plus 1. And all of that is being divided by pi. Well, 2 pi plus 1 minus 1 is just 2 pi, and 2 pi divided by pi is just 2. So our average rate of change on this interval is 2. And we'd like to know when is the derivative of this function equal to 2. So this will equal the derivative of f prime of x, and the derivative at some point, the derivative is 2 plus the cosine of x, and we want to know when that equals 2. Well, that will equal 2 when the cosine of x equals 0, and cosine on the unit circle, since it's an x value, is 0 at when x is pi halves, 3 pi halves, 5 pi halves, so on and so forth. Now on the interval where we're looking, our only possible answer is pi halves because we're restricted to 0 to pi. So that's the x value where the solution of the mean value theorem is. To write the tangent line, we'll need to know the y value. So our original function at pi halves is going to be equal to pi plus the sine of pi halves, which is 1 plus 1, or pi plus 2. So we have the point pi halves, comma pi plus 2, and we know the slope at that point is 2. Because we showed that the average rate of change must equal the instantaneous rate of change. So our tangent line would be y minus the y value, in this case pi plus 2, equals our slope times x minus the x value. And that's the equation of our tangent line.